Okay, so thank you. I was supposed to give a kind of pedagogical introduction, but actually it will be a combination of old things and relatively new ones. So, overview of certain things. And actually I would like to start with what we've learned yesterday, first from Yegor, then from Julian, and then from Vadim. So this type of exciting experiment, and in the context of this experiment, people typically use the following language. They discuss the phase which is called quartic metal. They call this phase a vestigial phase, and that's all true. So yes, it's a quartic metal given the structure of the order parameter. It's vestigial by the fact that it occurs at finite temperature, but actually those terms are too generic to explain what actually goes on, because remember what was discussed in terms of these nice colorful arrows is that actually there is something more than just broken time reversal, both superconducting in normal phase. Those three speakers were talking of vortices, the main walls, and somehow the very fact of breaking time reversal doesn't imply this interesting physics. So, long story short, there is some hidden order which is akin to topological order in the sense that it manifests itself in terms of the grain boundaries. So the key property of the state, actually both states which are referred to as quartic metal and superconductor with broken time reversal, is the fact that there are more than one domain wall, because if you break Z2 symmetry generically, you expect to have just one domain wall. Here, there are three domain walls. Moreover, if there is a symmetry between underlying three components, coming from three bands, all the three will be absolutely equivalent to each other. And the point is that there is a direct bosonic analog of this interesting physics. Moreover, the adjective vestigial is not necessary in this context because the phase with this particular property can be implemented as just the ground state. So the game plan is the following. So for a while I will forget about this thing. I will describe counterflow superfluidity. Most importantly, with three or more components, we will see that this is so-called Baromean counterflow superfluidity, which features some interesting properties. And then we will see that to understand the property of this phase, we need to make one simple step. We need to introduce just some couplings between components, and we will be essentially back to understanding the structure of those special orders. So two simple scenarios which lead to the counterflow superfluidity, which we also call supercounterfluidity. Of course, there are many more implementations, but for my purposes, it's just sufficient to mention two. So one was proposed by, actually both were proposed almost simultaneously in one and the same year, 2002. One was proposed by Yegor a bit earlier than our scenario with Anatoly, who is present here and was giving a talk yesterday. So I will be back to Yegor's scenario a bit later on one of the next slides. So this scenario which we discussed with Anatoly is very basic. It's essentially a scenario. It's this scenario which is very well known, which stands behind magnetism. It's the super exchange. So if you have two components on a lattice, think of an optical lattice, so those are the sides of optical lattice. You have two bosons, red and blue. The net filling factor is 1, or maybe 2, commensurate filling factor. To have strong enough interaction leading to Mortness. So the net flow is suppressed by Mortness, but you can do the super exchange illustrated here, and actually two guys can swap their sides, meaning that there is a mode which corresponds to the counterflow if we use the particle language. Equivalently, we can think of the spin language. But an important thing that this scenario works for 3 and more components, which will be crucially important for us. So that's why we should not just think of 2 components only. However, in terms of 2 components, there is a nice news, experimental news. Actually, the next talk by Zhensheng Yuan will be all about this nice first experimental implementation of this scenario. So now, Yegor's scenario, which can be classified as one of the simplest vestigial scenarios. Think of a stack of 2-dimensional superconductors, 2 or more. The guys are not talking to each other, so there is no Josephson tunneling between them, but there is a coupling via vector potential. So if we have a vortex in one layer, then we know that conceptually, if it's a superconductor, there is a sharp crossover rather than phase transition at high temperature, because the vortices have finite energy, though large enough. So there is screening. However, if we have a vortex in one layer, there should be a counterpart in the next layer, because otherwise there will be infinite energy due to the coupling by vector potential. So if vortices proliferate, they proliferate as a stack of vortices in all the layers. That's essentially the mechanism which suppresses the net supercurrent, so the state becomes normal, but it can support counterflows between the layers. Neutral counterflows. That's yet another scenario which is kind of equally important if you want to conceptually understand the origin of corresponding orders.
So the coupling, there's Josephson coupling?
There is no Josephson coupling.
But then what's the coupling through vector potential?
Vector potential is the long-range interaction.
Just B squared.
It's just the flux.
Just B squared.
No,
It's as strong as the vortex, just...
both phases coupled with the same A.
Just think of the magnetic flux being felt by the next layer. In the absence of the vortex, you have an infinite energy.
Oh, there's no integer, okay. Okay.
In the absence of the vortex, you would have an infinite energy. The only way to render the energy finite is just to have a vortex. So kind of it's a very standard scenario. Yet another kind of intermediate scenario is the following. And this scenario can be actually particularly important practically in terms of the experiments. So we do not need to have exactly commensurate filling. The filling can be slightly incommensurate. And then we just increase the temperature and do a vestigial scenario. But what is important is just vestigial ordering rather than kind of vestigial order, because the order is precisely the same as in the ground state when we have mod physics. So experimentally, it can be actually very optimal scenario, because with this scenario we can get the highest possible temperature and there is no need for the exact commensurability. It's interesting enough that in terms of the ground state we had first principle simulations, but we never simulated this scenario in the context of the experimental achievements, which we will hear after my talk. For Zhensheng, it's really important to perform finite temperature simulations just to guide the experiment to the optimal regime. Okay, so there is yet another interesting possibility. So yesterday, Chandra made a very good comment that actually superconductors are insulators in the bulk, as we all know. So the topological object, they are insulators in the bulk. And if we think about the bulk of the superconductor, which is a multi-component object, so think of the multi-component superconductor, the currents, so the Meissner effect, we can also call it Anderson-Higgs effect. So there are no currents, electric currents in the bulk. Superconductivity is all about the surface.
I thought it goes back to London.
Yeah.
It goes back to London.
So it was
London.
London's idea.
Yeah.
Okay. Anyways, so kind of thinking of a superconductor as an insulator in the bulk, understand, thinking of a multi-component superconductor, we understand that the bulk of a multi-component superconductor behaves as a counterflow superfluid if we have more than one component. So this is yet another very important scenario, and as I said, if we add weak enough Josephson couplings, we can still think of the bulk of a multi-component superconductor in terms of counterflow superfluid. So yet another and very relevant to this experiment scenario. So what are the orders? These were mentioned already. So essentially we have some field psi. It can be a microscopic field if we are talking of bosons. It can be a composite field on its own consisting of two fermionic operators. So those details do not matter. Like, for example, when we think of helium-4, we introduce just one field. Meanwhile, helium-4 atom consists of 6 fermions, if we do not count quarks, 2 electrons, 2 protons, 2 neutrons. But all this is relevant with the down folding, and we just deal with some field. So that would be my elementary field psi A, and it's not necessarily even quantum field, can be classical. So the idea of counterflow ordering is the following. So the expectation values of operators of fields are 0 for this or that reason, be it vestigial or Mottness. But the following guys are different from 0. And since those guys feature the phase, we can think of topologically non-trivial situations when, for example, we have either a vortex or just doubly connected region, and this relative phase, so now the individual phase is ill-defined, but the relative phase is well-defined, and we can do phase twist, just the standard topological classification for the states. Those are states with counterflow. But now comes an interesting question. So you see, if you have just 2 components, it's more or less the same as a single component with just relative phase. But what happens if we have 3 or more? So that's the nice paper by Yegor and his students, where they actually did first principle simulation of 3-component bosons on a lattice. They call this situation Baromean supercounterfluidity, because you see all the 3 components are important for each other. Only the sum of the 3 filling factors actually is commensurate, yields 1. And the supertransport becomes non-trivial. That's interesting that somehow, that was the way how we were thinking of the counterflow superfluidity until recently. So microscopically, we think pairwise, like any 2 components can do counterflow. And that's what is reflected in this abstract. However, relatively recently with Yegor, we understood that this microscopic picture changes dramatically when we do macroscopic description. So here is the explanation. So see, all the relative phases are well defined. So as I said, if we have just 2 components, that's easy. It's just relative phase between the 2. We do something like a torus or a vortex, and we have an elementary winding, which is 2 pi, so everything is quantized modulo 2 pi. But what happens if we have 3 or more components? Now, if we just think that 1 winds with respect to 2, now comes the question, okay, what happens with 1 with respect to 3, or 3 with respect to 2? It turns out that now the situation is different. And it turns out that elementary vortices or elementary counterflow supercurrent states actually correspond to one of the n components winding its phase with respect to the others, while the others are not supposed to wind their phase with respect to each other. So all of a sudden, we see that while with 2 components, there is only one type of vortices. With 3 or more components, the number of elementary vortices is exactly equal to the number of components. And that creates an intrigue, which is essentially the essence of Baromean ordering as opposed to just counterflow ordering. Obviously, the number of normal modes, the number of gold stones is n minus 1, because the net transport is suppressed. But the number of elementary vortices is always n. So here comes an intrigue of how do we actually describe such a ground state macroscopically, not just. Question?
Yeah, so the question, so in everything you're describing, there's not going to be Josephson coupling between.
It will show up later.
Okay, but up to now.
Up to
and
now,
for a
there is
while-
no Josephson.
So there's
coupling.
some mechanism that suppresses both Josephson coupling.
Yeah, just different colors. We are talking of bosons.
Yeah.
Just three types of bosons. Just imagine that they are just apples, oranges, and
Okay, they don't talk to each other. Okay.
and are not talking to each other.
Okay.
That's why I'm talking
They are
about.
talking to each other but conserving the numbers.
So it's U1 cross U1 cross U1 n
Right.
times.
Mhm.
We will introduce Josephson coupling later, but so
It's
far
more than super.
there is absolutely no Josephson coupling. Okay?
Boris, please. So,
Yeah.
did I understood correctly? You said that when you have three components, then you have three relative phase.
No, there are many relative phases, but only 3 elementary vortices. Because
Okay.
all elementary vortices have the following structure. Just one relative phase does 2 pi with respect to the rest. And the rest do nothing with respect to each other. Okay? And
Yes, but
elementary,
so you have three components, just two meaningful relative phases. Three relative phases are not all independent, so only two are independent.
yeah, they are not independent, and we are coming to that. They are not independent, but in terms of, we are coming to the classification in terms of modular arithmetic. You will see that they are not independent, but the point is that there are n elementary vortices. That's really important. But the phases are not independent. You are absolutely, and this is the intrigue, how to describe the system, but they are not independent, but have this kind of structure, and respect the symmetry between the components. That's precisely.
Can you
Yeah.
combine two of these vortices somehow to get the third?
You will see everything. Just stay tuned. So essentially, that's the intrigue. We want to do hydrodynamic description of this phase, respecting the symmetry. So if we have 3 or more components, we really want to respect the symmetry. And on the other hand, we want a macroscopic description, not just microscopic when we have lattice which arrests the motion. So we want a model, a Hamiltonian, classical field hydrodynamic Hamiltonian written in terms of the phases, just a standard hydrodynamic, almost standard, written in terms of the phases and conjugate variables, which are deviations of the densities from their equilibrium values in such a way that we reproduce this physics. And the key guiding principle is the so-called compact gauge invariance. So, because it might seem like an oxymoron when you have a translationally invariant Hamiltonian which somehow arrests the motion. It appears naively that it's just absolutely impossible to arrest the net motion if the system is translationally invariant. So, turns out there is a way out, which is compact gauge invariance, which I want to describe. So suppose our Hamiltonian, written in terms of the single component phases, which are supposed to be not well defined, but still suppose it's written in terms of microscopic phases. But suppose the Hamiltonian is written in such a way that it is invariant to the following transformation. So it's a sort of gauge transformation when we add one and the same phase field to all the phases. What is important, why we call it compact gauge transformation, that this guy, as opposed to the standard gauge transformation, which involves gauge field, there are no gauge fields, by the way, just this funny field phi. This funny field is allowed to have vortices. So as opposed to the standard gauge transformation when we add a regular field to the phase and then we have a vector potential, here there is no vector potential, and we are allowed to add absolutely arbitrary field, including including vortices. So that's why it's a compact gauge invariant. So this guy is compact, and that's why it's allowed to have vortices. It turns out that if we have a theory with this type of invariance, it's a symmetry. And this is a local symmetry, and as we know, any local symmetry by Noether's theorem leads to the local constraint. And this local constraint, which emerges from the symmetry of the Hamiltonian, is precisely what we need to guarantee to arrest the net flow. So this is a simplest implementation. So this hydrodynamic Hamiltonian, speaking generally, is not necessarily needs to be harmonic, but this is a harmonic version. So we have the following fields. We have the fields which are deviations of the density from some expectation value, from some equilibrium value. So this is the structure of the Hamiltonian which enforces compact gauge invariance. So the difference in terms of the gradients of the phase. The gradients of the phase guarantee U1 cross U1 cross U1 and times. And the difference of the gradients guarantees this compact gauge invariance. So if we add the same field phi to each theta, the Hamiltonian stays invariant. So if you write down the equations of motion, they would have just the standard hydrodynamic type of the system of continuity equations. These are continuity equations with the following currents. And if we sum up the currents, we will see that the currents sum up to 0, meaning that the net density doesn't change. This is precisely what we need. So that's how actually we can write the ground state theory of counterflow superfluids.
So it's a property of lambda alpha beta?
Say it again?
It's a property of lambda?
Absolutely not.
Or symmetry of alpha?
Those absolutely not. Those guys can be everything.
Okay, but
the
it's a
property
symmetric
of
matrix.
it's the property of only this difference. This can be absolutely everything. This is irrelevant. What is relevant is those differences.
But I guess it has to be symmetric matrix, that's why, right?
Without loss of generality, because you can always symmetrize it. Without loss of generality,
Yeah, okay.
you can always symmetrize
right.
this matrix.
I think the key thing is there is no gradient of, there's no term describing
but somehow
gradient of the phase
Leo
sum.
believes that
Yeah.
Something special should be said about the matrix. You can always
Well, I mean, to get the J's to sum up, that has to be symmetric, right? Is that what?
just look at this expression.
Yeah, it's symmetric.
Without loss of generality. If it's asymmetric, you can symmetrize it.
Physics changes.
No, the physics doesn't change because
Lambda alpha beta is not symmetric.
Yeah, the key, the
Wait,
key,
Couldn't write that term.
yeah, the key thing is,
asymmetric
yeah, the key thing is that there is no gradients of the phase sum.
You're dropping it out.
So you can add and subtract.
look at this expression. I can replace asymmetric lambda with lambda tilde, which will be symmetric.
Yeah.
This is the standard property.
Yeah, if you let's say if you add like vortex with phase winding in all phases,
Yeah.
it means like adding nothing, or it means.
No one understands that, but he
Yeah.
somehow believes that it's
No,
crucial
no.
that this matrix is symmetric. I'm
I just
saying-
mean if I sum up these J's in this form,
Right.
to get 0, I need to have a,
Okay, let me answer your question. I got it. If this guy would be asymmetric,
Right.
this term would be different. So this expression takes into account the symmetry.
right.
If it would be asymmetric, there would be two terms,
That's what I
and
mean,
then
yeah.
ultimately they would sum to 0.
Yeah.
So in this sense, you're absolutely right. So that this expression is written on the
Right.
assumption that it is symmetric.
That's right.
But this
That's what I
assumption
mean.
is not restrictive because you can always symmetrize your matrix
Sure.
and end up with the expression like that. So
Right.
thanks for the comment. It's a fair comment. This expression is written already under the assumption that the matrix is symmetrized, but this assumption is not restrictive. Okay, very good. So essentially, that's the theory, how it looks like. And that's what Julien was asking about, so how to classify the defects. Now the defects are not independent, because you see by the compact gauge invariance, we can always, so if we just classify the defects in terms of the individual phases, we understand that it would be multiple counting of one and the same defect, but the multiple counting amounts to adding this vector to all of the guys. So kind of the simplest way to classify the defects is just to write them in a kind of simple form in terms of the individual phases, but then take into account that the defects, which can be reduced to each other by subtracting a multiple of this vector, are the same. Here is an example. So if I have three distinct elementary defects, like this one, and this one, from a distance, they would look like the defect with this topological charge, which is equivalent to 0. So locally, there will be three vortices. Globally, they will be topologically neutral, and things like that. So if I have locally two vortices like that, from a distance, they will be looking like elementary anti-vortex. So that's essentially the arithmetic of the defects. So now, promised bridge towards the discussion of quartic metals and stuff. So the only thing we need to add, so suppose we have nice Hamiltonian which Yegor and his students simulated on a lattice, and we add just very simple term to this Hamiltonian. Now we have Josephson couplings. Now we have a term which mixes components. And the sign of this coupling is such that actually the phases want to be opposite. So the phase difference, the optimal phase difference would be pi if we have only two components, but we have three. And we need to find a compromise. This compromise was already discussed yesterday. So essentially, the phases want to do 120-degree angle, but we should keep in mind that each individual phase is not well defined because of the compact gauge invariance. So this picture can be deceptive in terms of thinking that each of the guys is well defined. No, they are not well defined, but the difference between them is well defined. So this is the ground state. So this is the ground state which features only this type of order parameter, which would be equivalent to the quartic metal. In this case, it's just this order parameter, which has imaginary part different from 0, because only the imaginary part corresponds to the continuously broken symmetry. The real part is guaranteed by the structure of the Hamiltonian and is not interested. So that's how we quickly promote the Borromean counterfluid to this type of non-trivial state, ground state, which we call Borromean insulator. And essentially, there is a hydrodynamic description of Borromean insulator, which sounds like an oxymoron, because what hydrodynamics of insulator can be discussed. But look, if we just upgrade our hydrodynamic Hamiltonian to this Josephson term, and just write down the equations of motion, they will also come as continuity equations, but now with the right-hand sides, which also would sum up to 0. So if Josephson couplings are not particularly strong, we have actually a theory which mesoscopically looks like counterflow hydrodynamics. So that's a very simple upgrade which takes us to the state in question. And this is just a reminder. Here I am citing the paper by Yegor and his, I guess, students. Maybe Julien was a postdoc. He was not a postdoc. So John was a student, I believe, right at the time. So essentially, what they discussed at finite temperature, but now we see that the very same picture takes place at 0 temperature as well, that actually there are 3 types of domain walls. So if we go from one domain, like that, there are only 2 domains, like that and like that. So we swap just 2 arrows. But when we go from one domain to another, if our domain wall is thick, meaning that our Josephson coupling is weak enough, we can go 3 different ways. And this is just one of the ways. And if we can go 3 different ways, we have 3 different domain walls. If there is a component symmetry, they are absolutely equivalent to each other. And here, how we arrive at the notion of a vortex. We just connect two different domain walls, and then it's guaranteed that at the point when they meet, so if it's a two-dimensional system, these are just two lines. If it's a three-dimensional system, these are two planes and just a line between them. So this object is topologically protected by the fact of the domain walls being protected by the domains. So that's essentially the vortices which were discussed yesterday. That's how they look like with, in the language of neutral bosons. Okay, so I have some time. Just well, that's how we get back to this picture, which I already mentioned. So now we understand kind of how to think of this picture. And I'm just reminding you that the bulk of the superconductor looks pretty much like Borromean insulating ground state, apart from the vortices which correspond to the quantized magnetic flux. So in terms of the domain walls, which we just discussed, and those vortices which are reinforced by domain walls, the bulk of the superconductor is pretty much the same as the phase which I called Borromean insulator. And if we just hit a little bit Borromean insulator, it crosses over to the Borromean metal. So as opposed to the phase transition here, if we do neutral bosons, so there are no two phases, like metal and insulator, just metal will be just Borromean insulator with some excitations. So let me spend, I guess I have 10 minutes to introduce you to our recent work with Yegor and Yegor's students, Alex and Igor, who are present here. So actually the very same language of compact gauge invariance allows us to construct the models for the Borromean supercounterfluids at finite temperature. And the principle is very simple. So we know XY model, which is a prototypical model for superfluids. So that's how we can generalize the standard XY model to the Borromean XY. So now we have this expression. So the differences of gradients are replaced by the differences of differences. So looking at this model, you see that yes, indeed, it's compact gauge invariant because you can add any phase to all the phases on any side. So now in this model, the object which we want to calculate is the composite density matrix. So the matrix which is written in terms of the relative phases. And in terms of the simulation, we can do the following. So this is the duality which Anatoly was mentioning yesterday. So any model which is XY type with phases living on sides can be actually rewritten exactly by doing Fourier. It's all about Fourier into the model which consists of oriented loops, and the compact gauge invariance in this language corresponds to the fact that whenever we have a line of one column going in one direction, there is a counter-propagating line in the opposite direction. And it's just an exact duality because from this model we can go back to the XY type model, so it's just one-to-one correspondence. And this model is particularly convenient for simulation with the worm algorithm. And actually, this is a typical configuration with the worm sector. So we have two worms, and the statistics of the distances between the worms just corresponds to the composite density matrix which I mentioned. So we have a direct access.
Another index.
Say it again.
Another index.
Another index one.
When you write down rho, the index was alpha alpha, but it should be alpha something else.
No.
So it's single component rho.
Oh. That's a good. So actually, it's not. that's,
Okay.
okay, but thanks for asking. So essentially that I just take one component as the reference frame, the nth one, and then the rest of the guys is calculated with respect to the, I went too fast, so thanks for stopping me. So it's alpha. It's alpha, yes, so formally corresponds to a single component, but relative to the nth one. So alpha cannot be equal to n, let's put it this way. But that's essentially the idea of this. So yeah, so this phi is not single component, it's actually the difference between single component theta and the theta which is selected as a reference frame. And so in this picture we sort of break symmetry in terms of the notation. But in this language, the nice feature about this language is the symmetry is restored because it's actually this guy's component. Okay, so let me see how much time do I have. Oh, I have quite some time to show the results. So essentially, the question is, do we have an interesting universality class of the transition? So there are reasons, I will be not mentioning them because we still need to figure out whether they are exact or not, that in 3 and high dimensions, the phase transition will be of the first order. So you go from Brownian counterfluid to the normal state by first order phase transition, which is not particularly interesting in terms of criticality. But in 2D, we have both the theory and simulations showing that it's a BKT type criticality with some interesting risks, especially, and this is actually our current work, if we slightly break the component symmetry. So it's essentially a set of vortices. If we have 3 components, we have 3 types of vortices. They are all talking to each other. So the system of our G equations will kind of involve those interactions between different type of vortices. But it's interesting that if we do just symmetric case, everything boils down to quite simple system of 2 equations, pretty much of the same structure as the Costas-Thouless original equations. There is an analog of universal Nelson-Kosterlitz relation, so kind of some interesting relationship between the asymptotic behavior of the composite density matrix. This is probably remember that in a standard Costas-Thouless transition it's 1/4. Here actually this guy gamma depends on the number of components. So that's the expression. And
But sorry, so you lose stiffness in all differences at once?
yes, because of the component symmetry. And
Okay, I
interesting.
mean, you can break that symmetry, but,
I'll tell you, heads up, so the work in progress,
Okay.
so unpublished results. If you slightly break the symmetry, you still lose everything at once. But I will not be discussing that. This is kind of unpublished result. But that's an interesting question. If you slightly do asymmetry, you still lose everything at once. It's an interesting result, directly following from RG. But here is the fully symmetric case. You are supposed to lose everything at once because of the symmetry. You lose everything at once, but when you lose everything at once, different pairs of vortices do talk to each other. So you lose everything at once, but not kind of independent. Let's put it this way. That's why we have a different critical relation. So
Yeah.
essentially, that's why this expression depends on that. And this is actually the demonstration how we are just at the critical point. We measure, roughly speaking, the reduced density composite density matrix, and those slopes just demonstrate that the different pairs are talking to each other. Okay, probably I will. Yeah, actually I'm done. And those are kind of 3 simple pieces of conclusion. So we have Brownian supercounterfluids, n-1 Phonon modes, and elementary vortices. So we have long wave description of Brownian states in terms of the compact gauge symmetric and component hydrodynamic Hamiltonians at 0 temperature effective actions, and statistical models at finite temperature. And we can easily promote bromine superconductors to what we call bromine insulators by essentially introducing just some couplings between the components. Thank you very much.
Any questions for Boris?